Study guide for test 2. Determine if these relationships are a one-to-one function. Answer with yes or no. So to figure these out, we can use the horizontal line test. If we draw a horizontal line and hit that line one time, we know its inverse is a function. And if the original is a function and the inverse is a function, then we have a one-to-one function. So I'm going to look at each one of these relationships and determine if the inverse is a function and therefore figuring out if it's a one-to-one function. So starting off, part A, I know by looking at this equation, it's a straight line because it's following the classic y equals mx plus b, which is basically the first function you ever learn about. Now that means we have a line that is straight like this. And if that's what my graph looks like, if I draw a horizontal line, I hit it one time. It doesn't matter where I draw my horizontal line, I always hit this one time, which means that the function that they are giving us plus its inverse will both be functions, which means yes, this is a one-to-one function. Our second one has absolute value signs. Now this is the first function we actually explored in Algebra 2 back in quarter 1, which means that that equation will create a V-shaped graph, you may remember from back in the day. Now, once again, I'm going to use the horizontal line test to figure out if its inverse is a function. So if I draw myself a horizontal line, I will hit it in two places. That's one too many, which means the inverse, which would look like this, will not be a function. And I know that because I can draw a vertical line to do the vertical line test, and therefore I know that the inverse here isn't a function. So therefore, no, this is not a one-to-one. Once again, I can always figure this out by drawing a horizontal line test. So, part C, I draw a horizontal line. I hit it here and here. That's two places. That means its inverse is not a function. Therefore, this is not a one-to-one. So, no. Then we have part D. Once again, draw a horizontal line test. No matter where I draw this line, I'm always hitting it one time, which means that its inverse is not a function. Therefore, it's not a one-to-one, so no. Okay, so continuing with problem 1, doing the same thing, but this time they've provided in terms of a table. So what I like to do, I don't really like my tables horizontally like that. I find them harder to read. So I'm going to rewrite this table vertically. So I have a 3, a 4, a 5, a 6, and a 7. And then -4, -1, a 2, a 5, and an 8. All right, so now I need to figure out, is the table I have here a function? And once again, the way you can figure out if that's a function by looking at this, you could graph it if you wanted to take the time. But a function would let us know that with this table, that I'm looking for any x's that repeat themselves. So far, none of the x's repeat themselves, which means this is impossible for it not to be a function. So the original is definitely a function. Well, if the original is a function, and an inverse is me taking all those x's and y's and flipping them, so now I would have -4 and 3, -1 and 4, 2 and 5, 5 and 6, and 8 and 7. Now I have the inverse table. I have to see if that's a function. Once again, I look at the x's, and I don't see any x's repeating themselves, which means this is definitely a function. There's no way it can't be. So if the original is a function, and the inverse is a function, then yes, we have a one-to-one function. All right, so let's take a look at part F. I'm going to do the same thing. I'm going to rewrite this as a vertical table. So I have -2, -1, 0, 1, and 2. And then I look at the y's. I got 9, 3, 0, 3, and 9. Once again, I look at the x's. I don't see any x's repeating, so this is definitely a function. But now I want to go ahead and make the inverse table. And once again, the inverse table is just switching all the x's and the y's. So this is a 9, this is a -2, this is a 3, -1, 0, and 0, 3, 1, 9, 2. So this time I go ahead and I look at the x's again. But I notice that my x's repeat themselves. So I start off here with a 9. This 9 gives me a -2, which means no matter what happens, this 9 is always supposed to give me a -2. But if you look further down, this 9, that's not giving me a -2. It's giving me a +2. That means this function is not working. This is not a function. It's not working. A function basically says if I have a 9 for x, then I should always get a -2 for the y. But that doesn't happen. When it's no longer working, it's not a function. So no good. So therefore, no, this is not a one-to-one because the inverse is not a function. Problem 2. Now they're going to want us to write inverse equations. So they're giving us the original, and we want to write the inverse. So step 1 will always be to switch the position of the x and the y. After that, step 2 is simply to get y by itself. And every equation is different, so you're just going to have to try to think on your feet on what's going to work to get that to happen. So in this scenario, I want to isolate my y, but currently I have a -1 near it. So I'm going to go ahead and I'm going to add 1 over to where the x is. Those are going to cancel out. So now I'm going to have x plus 1 equals 4 over y. I want to get y by itself. To do that, I need to get it out of the denominator. So I'm going to go ahead and multiply both sides by y. That means the y here and the y here are going to cancel. So now I have y times x plus 1 equals 4. I want to get y by itself, but I unfortunately put it next to an x plus 1. So I have to get rid of that x plus 1 by dividing by x plus 1. So now I'm going to have y equals 4 over x plus 1. And I have my inverse. Okay. Part B. Doing the same thing. Step 1, switch your x and your y. Once we've done that, we can see that the y is trapped inside of these parentheses, and we want to get it out because we want that y by itself. So we're going to do the opposite of a cube, and that is cube root, which means the cube and the cube root are going to cancel out, leaving us with a y minus 2. And over here, we're going to have a cube root of x. Now that we don't have that exponent, we don't need the parentheses anymore. And so now I'm going to get that y by itself by simply adding 2 to the other side. So now I'm going to have the cube root of x plus 2 equals y. And I have the inverse. Okay, continuing with question 2, part C. Step 1, we want to switch that x and that y position. So I'm going to put the x here. I'm going to put the y here. And I want to get y by itself. So I need to get rid of this fraction. So I'm going to go ahead and multiply both sides of my equation by the denominator. So this 3 is going to divide away that 3, simply leaving 2 times y plus 6. Still trying to get y by itself. So I'm going to go ahead and get rid of the 2 by dividing both sides by 2. So now I have 3 over x minus 4 over 2 equals y plus 6. Well, I want to get rid of the 6 to get y by itself, so I'm going to minus the 6 over. So now I have 3x minus 4 over 2 minus 6 equals y. And I have my inverse. Part D, step 1, switch the x and the y. We want to get y by itself, so I'm going to minus that 2 over. So we have x minus 2 equals the square root of y. But we want to get rid of the square root because we want to get y by itself. So the opposite of a square root is a square. So I'll be bringing in an exponent of 2. The square and the square root are going to cancel out. leaving a y here, and then we have parentheses x minus 2 squared. Problem 3, evaluating each expression. So there's two ways you can do this. You can use the guessing method that I showed you in class, where we rewrite this in exponential form, where we take our base, which is 7. What a log equals is always an exponent, so we don't know our exponent, but we want to figure it out. And that's going to equal the result, which is 1. So we have to figure out 7 to what exponent equals 1. That's 0. Remember, it's a bit of a guessing game, and as a little reminder, how you type that into a calculator to start your guessing would be 7 exponent, pick a number, don't care what number you pick, until you get the answer of 1. That's the guessing method. You could also go with the change of base formula that I taught you in class. And as a reminder, how to set that up in a calculator, you would type log, your result goes first, close those parentheses, divide, log, your base. When you type that into a calculator, it's going to tell you 0. All right, part B. You can do 2 to some exponent equals 32. Well, you can do a little guessing. 2 to the 5th power is 32. So log base 2 of 32 is equal to 5. Remember, a log is always equal to an exponent. For C, same idea. Don't let the fractions scare you. We have a base of 3 to some exponent that equals 1 over 27. Now, keep in mind that if you have a whole number for a base, but the result is a fraction, like 1 over 27, that's a big clue that whatever that number is, it needs to be a negative to create that fraction. So I need to really figure out 3 to what exponent gives me 27. A 3 would. And the reason why this works, as a reminder from your exponent properties in third quarter, if you have 3 to the 3rd power, you want a positive exponent, you would have to move it to the denominator. Then it's really just 1 over 27. That's why negative 3 as an exponent is our answer. Now, what with a fraction might scare some of you, so you may want to use your change of base formula. That's cool. This is how you would type it in to your calculator. You would go log, once again, your result will go first, 1 divide 27. Remember, this is the divide button in your calculator. Divide log your base. Don't forget to hit the log button to do this. And when you do that calculation, it will tell you negative 3. Then we have 1/2 to some exponent gives us 8. So 1/2 some exponent gives us 8. This time we have a base that is a fraction, and the result is a whole number, which means, just like last time, that exponent is going to need to be a negative to make this work. So I'm going to ask myself, 2 to what exponent gives me an 8? A 3 does. And once again, the reason why this works, because if I have this as my problem, I would distribute that exponent to each part. So I'd have 1 to the negative 3, 2 to the negative 3. But I want those exponents to be positive, so I flip their position. So it's 2 to the 3rd and 1 to the 3rd. Well, 1 to the 3rd is 1, and 2 to the 3rd is 8, which just makes 8. That's why this works. Once again, you can just start guessing in your calculator, just like I showed you. You type in 1 divide 2 exponent and start guessing a number until you get an 8. But if you don't like doing that method, don't forget you do have the change of base formula that you can use. And it would look like this in your calculator. Log, once again, the result goes first. Close those parentheses. Log 1 divide 2. And it's going to tell you negative 3. All right, problem 4. Use the change of base formula to evaluate. So this time, it's set up very specifically that you will not be able to guess your way to the answer. So we have to use our change of base formula. And once again, the way we set it up, we're going to do log the result goes first, divide log base 3. We just type that into the calculator. And we're going to get 1.8927. And so that's what our log equals. Just remember what this really means. This is saying that 3 to an exponent of 1.8927 is equal to 8. Now, of course, since we kind of rounded off our decimal here, it won't be perfectly 8 if you checked it, but it's close enough. All right, part B, same idea. We're going to do the change of base formula. So log, the result goes first, close those parentheses, log 1 divide 3. So we just type that into the calculator. Hold on, I messed up when I typed it in. And you're going to get a negative 2.09590. All right, we're going to be graphing log base 3 x minus 2 and its inverse. So the first thing I want to do is figure out where my asymptote is. An asymptote comes from inside the parentheses of a log. We ask ourselves the question, what number minus 2 equals 0? That would be positive 2. That asymptote is x equals 2. Put that over there next to our key features. Then we need to go ahead and make a table. Now the table we're going to make is not going to be for the equation they're giving us. I'm going to make a parent function table where it's log base 3 of x, where I'm going to use the reciprocal of the base, 1/3, the number 1, and the base itself. If you always use the reciprocal, the 1, and the base, you will always end up getting -1, 0, and 1 for the tables. Now, keep in mind, that table I just made is not the one that I'm graphing. I have a transformation here. I have the x minus 2. That makes my asymptote go to the right. It makes all my points go to the right, because that's our h value. Well, if I'm moving to the right, I'm moving towards positive numbers. So I'm moving towards the positive numbers, and that means I have to change the x values because I'm shifting everything to the right. So I'm going to add 2 to each one of my x's in my column. So 1/3 plus 2 is 2 and 1/3. 1 plus 2 is 3. 3 plus 2 is 5. Nothing's happening to the y's because we're not moving the graph up or down, only to the right. So I'll have 2 and 1/3, -1, 3, 0, 5, 1. Then I connect the points, don't pass the asymptote, like so. Well, now that we have our graph, our directions ask us to graph the inverse. That's what our next table is for. Well, to graph our inverse, we need to go ahead and know what kind of graph we're really looking at. Well, we have a log. Which means a log's inverse is an exponential. An exponential, 3 to the x, blah, 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 blah. Well, if it's an exponential, we know exponentials look like this with an asymptote. Okay, well, if we make an inverse by switching the position of the x and y columns, well, that's also going to be true for the asymptote. So if our asymptote for the log is x equals 2, then the asymptote for the exponential is y equals 2, because the x and y switch. So I know my asymptote will be right there for the exponential. So now all I need to do is switch the x and y values in my red table. So this is going to be -1, this is 2 1/3, this is 0, this is 3, this is 1, this is 5. And now I have the table for the inverse. So now I'm going to plot those points. So -1, 2 1/3, 0 and 3, 1 and 5. Once again, don't pass the asymptote, and you've graphed your inverse. So the last thing it's asking us to do is to state some key features for that log graph. That's the first graph we did over here. First thing it's asking for is domain. Well, we have an asymptote at 2, and we can't touch the asymptote, so it's using everything that is after 2 and beyond. So like 2, 3, 4, 5, all numbers greater than 2. So x is greater than 2. The x-intercept, we can see that's right there at 3, 0. And the right in behavior. So we're talking about this side of the graph, which means as x approaches infinity, because it's heading towards positive infinity, the y value, you can see the graph is pointing upwards, is heading towards positive infinity. Problem 6. We're doing another graph and then graphing its inverse. So we're going to start off with figuring out what our asymptote is. We look inside the parentheses, we ask ourselves what number plus 4 would equal 0? Well, that's going to be -4. So we are going to have an asymptote at x equals -4. Well, now that we have that, we need to make our table. So our table is going to be for the original, which will be log base 5 of x. So since I have a 5 for a base, its reciprocal is 1/5. I'll always use the number 1, and then I'll use the base itself. When I use those numbers, the y values will always be -1, 0, and 1, every time, forever and always. Now keep in mind, I'm not graphing those points. Don't you do it. Don't you do it. I know you thought about it. Don't you do it. Instead, we need to add in these transformations. We have an h and we have a k, which means we need to make ourselves a new table. And if we have x plus 4, we are changing things on the x-axis. You can see this time our asymptote is to the left of 0. It went left. That means we need to be minusing 4 units to move our graph to the left. So all of my x's are going to get a -4. But I have a k this time. K moves graphs up and down. And therefore, I have to add 2 because I have to move my graph up too. So now I need to go ahead and do a calculation. I'm going to do 1/5 in my calculator minus 4. I'm going to get myself -3.8. Then I'm going to do 1 minus 4. I'm going to get -3. And then 5 minus 4 is 1. Now I'm going to deal with the y's. I have -1 plus 2. I get a 1. 0 plus 2 is 2. 1 plus 2 is 3. The blue table is the one that I'm graphing. That's the inverse that they're asking me to graph. So I'll do that the best I can. So -3.8 and then +1 will be roughly about there. -3.2 will be here. And then 1 +3 would be right here. So once again, don't pass the asymptotes. And then we have our graph. Well, remember the question is also asking us to write the inverse. So therefore, if our asymptote is x equals -4, and when we write an inverse, all the x's and y's switch positions, that means our asymptote is going to be at y equals -4. Now we can go ahead and switch the position of all the numbers in the blue table. So 1, -3.8, 2, -3, 3, and 1. So I'll be at 1 and -3.8, 2 and -3, and then 3, and then +1. And now I just draw my exponential, like so. Now for the key features. These are the key features for the log graph. So this time our asymptote is at -4, and you can see the graph is to the right of -4. So we're using all the x values that are greater than -4. Our asymptote we know is x equals -4. Don't forget the x equals. Our x-intercept. We cannot really see what the x-intercept is, so I forgot to change that. We don't have to worry about the x-intercept there. Don't worry about it. If that shows up on your test, you'll be able to see it just like in problem 5. The right end behavior, so once again, we're looking at this side of the graph where x approaches infinity. And since the graph is pointing up, the y will approach infinity. Right? Condensing logs. So this is using our properties of logs. So when you're condensing logs, usually the way it works is that you're probably going to start off with the power property. And that's the power property is when you're taking the numbers that you notice that are in front of your logs, which is like the 4 and the 12 here, and you move them into the exponent position. Sorry, I'm having some trouble with my pens. Into the exponent position. So I'll always start off with the power property. After the power property, you're going to basically end up in two different situations. You're going to be using the quotient property or the product property. They're really much the only options you got. So I'm going to start with part A. I'm going to take those numbers that are in front of log. I'm going to move them into the exponent position. So it is log base 8, a to the 4th power, plus log base 8, b to the 12th power. Once you have that, we have utilized the power property. Well, I have a plus sign. Plus sign goes with product. If it's a plus, you can rewrite it as a times, a product. Log base 8, a to the 4th, times b to the 12th. And now I have a single log. I have condensed it the best that I can, and I will leave it the way it is. Part B. Once again, I have a number in front of the log. It's going to get moved to the exponent position. A number in front of the log, moving to the exponent position. Once again, using the power rule, the power property. So I have log base 4 of 8 to the 15th minus log base 4 of 5 to the 5th. From there, I have a minus, and minus goes with the quotient rule. So I'll write a single log as log base 4, 8 to the 15 over 5 to the 5th. You do not have to figure out what 8 to the 15th is. That is a very large number, and I do not want to see it. This is what I'm looking for. Part C, same idea. You're going to take those numbers in front of the logs and move them into the exponent position. So you have log base 5, 7 to the 3, and then plus log base 5, 10 to the 1/2. We're going to write it as a single log. We have a plus, so we're going to use times. So we have log base 5, 7 to the 3 times 10 to the 1/2. Now, we're not going to leave it as a 1/2. We can rewrite that as a radical. So we're going to go to log base 5, 7 to the 3, and then the square root of 10. And it's the square root of 10. As a reminder, the top number is your exponent. The bottom number is your index. The index is this little guy right here, and the exponent is a 1, but we don't really need to write that because we can put invisible 1s for exponents. So your answer should look like this. Okay, problem 8. We're going to expand the logs. So this time, it does the reverse order. When you're expanding, you're starting off with the quotient rule or the product rule. Then you're going to go to the power rule. So in this case, I have a divide. When you see it as a fraction, it's a division, which means that's quotient. And that means if we expand it, it turns into subtraction signs. And now I'm going to apply the power rule by moving my exponents to the front of the log. So I have 7 log base 3 of x minus 3 log base 3 of y. And I've expanded the log. Part B. To start off with, I'm going to rewrite that radical as a fractional exponent. So I will have log base 2 of 3 times x. They're invisible 1 for the exponent. It goes exponent over index. And now that I see my time sign, I will then use the product rule. So I have log base 2, 3 plus log base 2 x to the 1/4. Now, this time, only the x has a exponent, so it's the only thing that's going to get moved to the front. So I have log base 2 of 3 plus 1/4 log base 2 of x. And I've expanded. All right. Now we're going to be looking at solving equations. Our first one is an exponential. So solving an exponential, the thing we want to try to do is get the bases to be the same. So in this case, we definitely can. We have a 25 and a 5. I know I can rewrite 25 as 5 to the second power. Those are equivalent to each other. So that means the way I can rewrite my equation would look like this. And then we can use something that we talked about in class called the one-to-one property, or sometimes the textbook calls it the equality property of exponents, I believe it is. Well, all that simply means is if the bases are the same, like 5 and 5, we can ignore them, which is the reason why we turn 25 into a 5 squared. And we can just set the exponents equal to each other and solve that equation for x. So 2 times 2 and 2 times 2x, I'll have 4, and negative 4x equals 3. I will minus this 4 over, and I will get negative 1. Then I'm going to divide both sides by negative 4. So I have x equals 1/4. Part B. So we have two logs here, a log equal a log, and if the bases are the same, which they are, you can use that one-to-one property. Since logs are inverses of exponentials, that property still applies. If the logs with the same bases, if they're the same, you can ignore them and set their results equal to each other. And then you can solve for x. So I can go ahead and I can minus the 2x over. So I'll have an x here, minus 5 equals 9. I'm going to add the 5. So I have x equals 14. Okay, so this one says solve the equation. So we have some log equations here, but this time you'll notice that both sides of the equations don't have log in it, which means we can't use that one-to-one property to be able to ignore the logs themselves. So instead, we are going to rewrite it as a exponential. But I first need to make sure that there is nothing in front of the log and there's nothing behind the log on the left side of this equation. So I don't have a number in front of the log. There's nothing in front of log. There's nothing behind the parentheses and between the equal sign. So I'm good. I can now safely put this into exponential form. Remember, this is your base. This is your exponent. And this is what I like to call the result. So I will do 6 to the second power equals x plus 1. It's now in exponential form. Now I can solve this equation. 6 to the second power is 36. I then want to get x by itself, so I minus the 1 over, and I see that x is equal to 35. And I've solved the equation. Next problem, part D. Once again, going to do the same thing, but I need to check to make sure there's nothing in front of the log or nothing behind the log. So I notice I have something in front of the log. I have a negative 2. This is negative 2 times log base 9 of 9x. So I need to get rid of it by undoing that times by dividing. So we're going to have log base 9 of 9x equals negative 8 divided by negative 2 is 4. From here, just going to rewrite it in exponential form. 9 is my base, 4 is my exponent, that equals 9x. 9 to the fourth power is 6,561 equals 9x. I'm going to divide both sides by 9, and I learned that x is equal to 729. Okay, one of our review problems from the last test. So they want us to write an exponential in the form of y equals ab to the x, which means we know the asymptote is 0. We can see it in the graph. It's right here. And they're also not saying plus k, so we know we don't have to worry about asymptote things. Now, as a reminder, a is your y-intercept, and b is the rate of growth or decay. Now, looking at this particular graph, this is a growth graph. It starts small and gets bigger and bigger and bigger. But we need to figure out what that number is. So to do that, I'm looking for two coordinates that are next to each other. That would be B and C. And I know they're next to each other because the x is 1 and then the x is 2. Notice point A is at -1. The next point over would be 0 something. We don't have that. That's why I'm not going to use A for this. I'm going to use B and C. So when I want to go ahead and find B, which is the same way I find R when we used to do geometric sequences, same thing, I'm going to go ahead and I'm going to take the y value furthest into the exponential, which is the 24, because the coordinate 2, 24 is further along the line of the exponential than 1, 6 is. I'm going to take the 24, I'm going to divide it by the y value before it, which is going to be 6. 24 divided by 6 is 4, which means the b is 4. This is multiplying by 4 every time. Okay, so if that's the case, I need to figure out what a is. I can't see what the y-intercept is. It's some kind of decimal. So I'm going to go y equals a, parentheses, 4 to the x. Well, to solve for a, I need to know what x and y are. Well, I can pick those numbers. I have two really nice points here. I have 2, 24 and 1, 6. And it doesn't matter which one you pick. I'm going to pick this one because I know that x is 1 and I know the y is 6. So I'm just going to go ahead to this equation. I'm going to make the y a 6. I'm going to make the x a 1. And I'm going to solve for a. 4 to the first power is 4, so I have 4a equals 6. I'm going to divide both sides by 4. So a equals, I can reduce this down to 3 over 2. You could also call it 1.5 if you prefer decimals. So your answer is y equals 1.5 times 4 to the x, or you could write it as y equals 3 over 2 times 4 to the x. Same thing. All right, last problem, one of our review questions from the last test. We have ourselves a sequence. They tell us it's arithmetic. They give us two different terms, and they want us to find the common difference. So once again, you're basically using the slope formula. You're taking your two term values, 235 minus 82. And then we're going to divide, and then we're going to take the term positions. We're going to do the 30th term minus 13th term. We're going to get 153, and then we're going to get 17. That's going to divide to give us 9. So we know the common difference is 9. That means it's going to take, every time we go from one number to the next in this sequence, we're going to add 9 to build the sequence. We need to figure out what term 1 is. We can do that by using the explicit formula. We know the d is 9. We need to choose whether we want to use a sub 13 equals a2 or a sub 30 equals 235. I'm going to use this one right here just because the numbers are smaller. That means the 13 is going to be the n, and the 82 is going to be the a sub n. So I'll have 82 here, and I'm going to have 13 there. So 13 minus 1 is 12. And then 12 times 9 is 108. And then 82 minus 108 is going to be Negative 26 equals a sub 1. I have my first term.